Have you ever really stopped to think about the invisible forces that make our modern world even possible? I mean, from the lights in your room to the phone right in your hand, it all runs on this secret, incredibly powerful partnership. All right, let's dive in and uncover the amazing connection between electricity and magnetism. It all starts with something we've all seen. You're looking at iron filings, and they're revealing this hidden, beautiful field all around a simple bar magnet. It's a force we've all played with, sure, but how does it actually work? And what in the world does it have to do with electricity? First things first, let's get the basics down. To understand the partnership, we really need to understand the partners. And we're going to start with the magnet. Okay, so every single magnet has a north and a south pole. The old saying is true: opposites attract. These invisible magnetic field lines are always flowing from north out to south. So if you bring a north pole near a south pole, they pull right together. But what happens if you try to force two north poles to touch? Nope, they push apart. It's a fundamental rule of how our universe is put together. All those lines we were just looking at, they actually have a name: magnetic flux. The easiest way to think about it is just the total amount of magnetism coming from the magnet. So the more lines you have crammed into one area, the stronger that magnetic force is going to be. Simple as that. So we've got our magnet, but where does the electricity fit in? Well, this is where things get really interesting, because it turns out these two forces aren't just, neighbors. They literally create each other. And here it is, the core secret of this whole partnership. An electric current doesn't just flow through a wire. It creates an invisible magnetic field all around it. They're totally inseparable. You literally cannot have one without the other. And this field isn't just random either. It's perfectly predictable. There's even a pretty cool trick to figure out its direction. It's called the right-hand rule. Just point your thumb in the same direction the current is flowing, and your fingers will naturally curl in the exact direction of the magnetic field. It's a direct, physical, one-to-one relationship. All right, so knowing that electricity creates magnetism is cool and all, but what can we actually do with it? Well, it turns out this partnership is the engine behind almost every major piece of technology that we rely on every single day. Let's kick things off with one of the most important applications there is: the transformer. Seriously, without this, our entire global power grid would just be impossible. Transformers use this absolutely brilliant trick. We know a steady current makes a steady magnetic field. But what happens if the current is constantly changing? Well, you get a constantly changing magnetic field. And here's the magic part. That changing field can create or induce a voltage in a completely separate nearby wire. No physical connection needed at all. This is how we can efficiently move electricity over huge distances to power our homes. Okay, next up, motor action. How do we take all this electricity and turn it into actual physical movement? I mean, think about everything from a simple little fan to a massive electric car. The principle here is so elegantly simple. You take that same wire with current flowing through it, and you stick it inside another magnetic field. The two fields then interact. They literally push and pull on each other. And this creates a real physical force on the wire. If you can harness that force with a spinning shaft, boom, you've got an electric motor. So we can turn electricity into motion. But that brings up the biggest question of all, doesn't it? How do we even create the electricity in the first place? Well, that is the basis of generator action. And it turns out we just have to flip the whole motor principle right on its head. Instead of using electricity to make something move, we use motion to create electricity. By physically pushing a wire through a magnetic field, we actually force the electrons in that wire to move. And that flow of electrons, well, that is an electric current. This one idea is the foundation of pretty much every power plant on the entire planet. Now, trying to design things with all these invisible forces flying around sounds incredibly complicated. But engineers came up with a fantastic way to think about it by comparing it to something much, much simpler: an electric circuit. So to get this analogy, we just need one new term: reluctance. In an electric circuit, you have resistance, which, well, it resists the flow of current. In a magnetic circuit, reluctance is what opposes the flow of magnetic flux. So some materials, like iron, have super low reluctance, while something like air has a really high reluctance. And this is where that analogy just clicks into place beautifully. In an electric circuit, the push is voltage, right? Well, in a magnetic circuit, it's called magnemotive force. The flow in electricity is current. In magnetism, it's that magnetic flux we talked about. And the opposition to that flow? It's resistance versus, you guessed it, reluctance. By thinking this way, engineers can design incredibly complex motors and transformers using the same basic rules you'd use for a simple circuit. It's genius. But this force, as powerful as it is, well, it isn't infinite. There's a very real physical limit to how much magnetism you can actually cram into a material. This graph, which is called a BH curve, shows us exactly what that limit looks like. Down at the bottom, that's the effort, the electric current we're putting in, and on the side, that's the magnetic field we're getting out. Now at first, it's a great deal. A little bit of effort gets you a whole lot of magnetism. But do you see how the curve starts to bend and then just flattens out? That's called saturation. So here's the really crucial point. Once a material is saturated, you can pump in tons and tons of extra electrical energy, but you get almost no extra magnetic force back. It becomes incredibly inefficient. It's kind of like trying to pour more sugar into a glass of iced tea that's already full of sugar. It just settles on the bottom, it doesn't do anything. So engineers have to design their motors and transformers to operate right near that knee of the curve to get the most bang for their buck without wasting a bunch of energy. So from generating power to making things move, this incredible dance between electricity and magnetism is fundamental to our entire way of life. It's this invisible partnership that has built our whole modern world. So the only question left is, what new technologies will we unlock with it next?